Yes, so thank you. I would like to start by thanking Uriel, Rahul, and Kostya for organizing this meeting and for inviting me to give a presentation. Also, thanks a lot to the ICTS staff, which, as it was shown right now, they are extremely helpful and effective and efficient. And so the work that I'm going to present is a collaboration with John Gibbon, and who just gave a talk. And this work actually relies heavily on the techniques and methods that John has just presented. And as the title says, it's an attempt to establish a rigorous quantitative comparison between shell models and the 3D Navier-Stokes equations. So of course, I do not need to introduce shell models to this audience, but just a few words to set the framework. So shell models are systems of ordinary differential equations where the variables uj are complex variables which loosely represent the Fourier amplitudes of the velocity. And the number k's are interpreted as wave numbers. They play the role of wave numbers, and they are spaced logarithmically, so that one can achieve a very wide ranges in wave numbers, which means very large Reynolds numbers. And the structure of the equations resembles that of the Navier-Stokes equation in Fourier space. Indeed, there is a nonlinear term where the interactions are restricted to the nearest terms, or to the nearest neighbors, or to the next two nearest ones. And there is a quadratic dissipation plus a forcing. So these systems have played an important role, especially in the 80s, the 90s, where direct numerical simulations at very large Reynolds numbers were impossible or extremely challenging. With these models, it was possible to reproduce the phenomenology of isotropic turbulence at large Reynolds numbers. And for example, one of the issues that was studied with this these systems are the presence of anomalous scaling in what are the analogs of the structure functions of the velocity. Then shell models are not restricted only to hydrodynamic turbulence. There are generalizations which apply to magnetohydrodynamics, convection, drag reduction in polymer solutions, binary fluids. There is a variety of these shell models. And for those who might be less familiar with them, here are some books and review papers that introduce shell models in detail. Now, more recently, but already now 10 or 15 years ago, shell models have attracted the attention of mathematicians also. This is because the analysis of shell models is simpler than that of the Navier-Stokes equations. And also several regularity properties can be proved for the shell models, whereas they still remain open questions, and I would even say major open questions for the 3D Navier-Stokes equations. In particular, in these two papers, Konstantin, Levant, and Titi have given a full study of the regularity properties of the Sabra shell model. And for example, they proved existence and uniqueness of weak solutions, the strong solutions, and the fact that if the forcing decays exponentially with the wave number, also the velocity variables decay exponentially. And as Idris reminded us last week, this is an indication of the existence of a viscous scale and therefore a viscous range. And for example, another thing which was proved in those papers is the existence of a global attractor, the dimension of which was estimated with lower and upper bounds in the same papers, and the existence of an inertial manifold, which once again, Idris reminded us last week, means that the dynamics of the system can be described by a finite number of variables. An analogous study of the regularity properties of shell models was given in this paper by Flandoli and collaborators in the case where the forcing is not deterministic, but stochastic. And also inviscid shell model have attracted attention in the case when the viscosity is 0. And there is a similarity in behavior with the Euler equations. For example, in this paper, again by Konstantin, Levante, and Titi, it was proved, it was introduced the analog of a BKM criterion for blow-up. And it was proved that the von Sager conjecture for shell models, that is when the velocity variables decay as kj to the power minus 1/3, these solutions conserve energy. And in this set of papers, Flandoli and collaborators have studied, again, the inviscid shell model. They showed that there can be dissipative solutions, which the energy of which decay in time, despite the fact that the viscosity is 0. And they also showed in this last paper that the presence of a stochastic forcing has a regularizing effect on the solutions when viscosity is absent. Now, the question that we are going to address, and that I mentioned at the beginning, is can we find a way to make a quantitative comparison between shell models and the Navier-Stokes equations? Of course, stated in this way, the question is very vague. So what kind of approach are we going to take? We are going to compare how the velocity derivatives and their moments depend on Reynolds in the two systems. So as John has explained in his talk, there is this extremely general result which encompasses a lot of previous results in the literature, which tells us how the nth derivative of the velocity and its 2nth moment depend on the Reynolds number. This on a periodic domain and for several values of integer n and m. So the question is, can we try to obtain similar estimates for the shell model analogs of these quantities and compare the dependence on Reynolds of the two? So before I come to this, of course, the study, I want to mention that the study of velocity gradients and their movements in turbulence is not a new question. It is indeed well known that the moments of the velocity gradient scale as the Reynolds as a power law of the Reynolds number. And in this famous paper by Nelkin, a relation was given between chi p, the scaling exponent for the gradient, and the scaling exponent which gives the anomalous scaling of the velocity structure functions. Then the same quantities have been studied numerically in direct numerical simulations of Navier-Stokes and in the Burgers equations. So I would like to stress that the quantities that were already discussed by John and that I'm going to discuss are slightly different from these ones because of this reason. So on the one hand, we are able to raise the derivative of u up to higher order. We can take n greater than 1 and take moments of these quantities. But at the same time, we have to include an exponent between the space and time average, which decreases with n. This is needed to achieve finite bounds for these quantities. At the same time, it is perfect, and it makes perfect sense to make the comparison between the shell model and the Navier-Stokes equations based on these quantities here. It's an alternative object to study. So let me come back now to the shell model and define introduce the definitions and make the assumptions I'm making in a clearer way. So I will consider the Sabra shell model, but I would like to mention the results are completely general in the sense that they also hold exactly the same for the GOI model, only the numerical coefficients in the estimates will change. And so other shell models with similar structure would yield the same results I'm going to show, especially in terms of scaling with the Reynolds number. Now, regarding the energy of the system, it is defined in the usual way. I'm making the assumption that the coefficients A, B, and C sum up to 0. Indeed, this implies energy conservation. Then in applications, usually additional choices are made in the sense that for the values of A, B, and C, and according to the choices, one can have a laminar kind of behavior or a chaotic one. One can have a direct energy cascade or an inverse energy cascade, but I will stay general and only consider this condition. No other condition are applied on A, B, and C. And of course, I mean, this is not surprising. I'm assuming that at the beginning, this sum converges. Now, regarding the forcing of the equations, I'm distinguishing the magnitude, capital F, from the shape of the forcing. And the shape is such as there are two numbers, JF and Jmax. Below JF, Fj is 0, Phi-j is 0, and of course also Fj, and above Jmax, it is also 0. So this is a narrow band forcing, which is perfectly compatible with what is usually used in simulation. And the existence of this tells me that there are two characteristic wave numbers in the forcing, Kf, and the max. I mean, the characteristic wave number Kf and the maximum wave number Kmax. In principle, I would not need to assume this for all the results that I'm going to present, but it doesn't matter it's not necessary to be fully general. This is perfectly, it has a physical sense. So let me say that under these assumptions, as I mentioned in the paper of Konstantin, Levant, and Titi, it was shown that the UJs decay exponentially fast. Therefore, all the steps that I'm going to make are completely safe. All the manipulations I'm going to make are completely safe from the mathematical point of view. And in particular, I can define a time average up to t of the energy, which gives me a root mean square velocity u, with which I can define a Reynolds number in the usual way, and the Grashof number, which, as John also recalled, is a dimensionless measure of the magnitude of the forcing. Let me also say that this average here is up to time t, is a finite time average up to a possibly very long time, capital T. And the estimates that I'm going to show will also be followed by numerical simulations in a setting which is completely standard. So here are the usual choices for the coefficients. It's forcing, the system is forced on the first shell, and the number of shells is varied according to the viscosity, and the integration scheme is also well known. So now that we have this framework, what kind of strategy are we going to take to estimate the velocity derivatives and their moments? So the strategy is adapted from the one available for the 3D Navier-Stokes equations, which was also mentioned by John in the talk, and which is summarized in his book. And this consists in starting from the low order derivatives, estimating the lower order derivatives of the velocity, and then using these estimates to climb up to higher order derivatives and their moments. Of course, in doing this, the approach is much easier for the Navier-Stokes, for the shell model than for the Navier-Stokes, because in the case of the Navier-Stokes equations, one deals with differential inequalities, whereas here for the shell model, we are dealing with the inequalities between sums. So let us now take this approach and start, therefore, with a low-order estimate of a low-order derivative, which will simply be the energy dissipation rate. This is defined as usually as the time average of the entropy with multiplied by viscosity. And this is the estimate that we have proved, where we can distinguish a laminar regime, which scales as Reynolds squared, and the turbulent regime, which scales as Reynolds cube. Quantity is rescaled in the more familiar way, where epsilon is divided by u cube and kf, which shows that the energy dissipation rate tends to a constant where the Reynolds number is very large. Let me also say that the constants here, and this holds for all the constants in the talk, they can be calculated explicitly for the shell model. Whether they are optimal is another problem, but they can be calculated explicitly. And they only depend on the parameters of the shell model, which are A, B, C, the coefficients, and lambda, which defines the wave numbers, and on the shape function, which determines the form of the forcing. But they are independent on physical quantities like the viscosity, the largest wave number, the wave numbers in the forcing, and the magnitude of the forcing. These quantities either appear explicitly in the estimate or inside the dimensionless numbers. So at this level, there is nothing very surprising. It agrees with what is known from physical arguments. And we also know that the perfectly analogous estimate exists for the three-dimensional Navier-Stokes equations. This estimate was obtained by Doring and Foyas in this JFM paper in 2005. And actually, to prove this for shell models, we really borrowed the same methods from the paper of Doring and Foyas. So at the level of the energy dissipation rate, there is very good agreement between the shell model and the Navier-Stokes equations. Let me, before we move to higher order derivatives, let me just mention one thing, which is again something related to what John was discussing in his talk. This inequality can be simply rewritten as a relation between the Grashof number and the Reynolds number. And as John was saying, this is interesting at least for two reasons. The first one is that the Grashof number describes the input in the system. It describes the forcing which we give in the problem, which we define. And the Reynolds number is how the system responds to such a forcing. And the second reason is also that usually mathematical estimates are done in terms of the Grashof number, because the forcing is what is controlled, what is known a priori, whereas the physical estimates usually are based on the Reynolds number. So such a relation is useful because it makes a connection between the mathematical studies and the physical ones. And it is also for the shell model very nicely reproduced over a wide range of scales. And once again, this is obviously the same in the 3D Navier-Stokes equations. So it was obtained in the same paper. So up to this level, there is a nice agreement, a nice parallel between the two systems. Let us now move to higher order derivatives. So now we consider this sequence of quantities, Hn, where I'm raising here the power of kj, which means I'm raising the order of derivation, of differentiation. And by taking the sum, this is basically the space average of the nth derivative of the velocity to the power 2. In this sequence, the first or the 0th term is the energy, total energy. The first term is entropy, its time average gives the energy dissipation. And of course, going up, one can have H2, which is palistrophy, etc. Now, it is possible to, we have been able to prove that these quantities satisfy a set of differential inequalities which relate Hn, which n plus 1. So these inequalities contain the essence of the strategy I was describing because of this, of the following reason. Imagine loosely we are taking a time average of this inequality. Then the time derivative will average it to 0. Then I can move this term to the right-hand side, the Hn plus 1 term, sorry, on the left-hand side, and therefore it will be controlled by what is left on the right-hand side, which only depend on Hn. So if I can estimate Hn, I automatically get an estimate for Hn plus 1. And I can therefore climb to higher order derivatives. Here, I forgot to mention this phi n is something completely innocent. It's just the equivalent of Hn for the forcing, where U is replaced by F. So it's something which is completely controlled. So is there something similar, similar structure for the Navier-Stokes equations? Yes, there is. And it was proved in this paper by Bartuccelli, Doering, and Gibbon. So of course, the equivalent quantities of Hn are these ones. And a perfectly analogous relation holds for the Hn, where here we have the infinity norm of grad U, but this is the same as, I mean, it's the analog of this, the soup of Kj of Uj, it's the maximum value of the derivative. So perfect analogy again. Now let us see what is this. I mentioned this strategy using, so we know H1, we have an estimate for the time average of H1. We can use it to move to higher order derivatives, and let us see what we get. So we obtain for the Hn of higher order that the time averages are bounded by Reynolds to the power cube with an exponent which depends on n and which is 2 over n plus 1. As you can see, this is a high Reynolds number result, and indeed it only holds at very high Reynolds for different orders of derivation, of differentiation. At lower Reynolds numbers, there is a different dependence on the Reynolds number for each order of differentiation. But this is also something which can be understood within the proof. So now how this estimate compares with what we know for the Navier-Stokes equations. So now we start seeing a first difference between the two systems. For the 3D Navier-Stokes equations, we have this estimate, which goes back to Foyas, Guillaume, and Themen. As I mentioned, the Hn in the 3D Navier-Stokes equations are the space integral of the nth derivative squared. We have that in both cases, Hn are bounded, the time average is bounded by Reynolds cube, but the exponents are different in this case. And the exponent for the 3D Navier-Stokes equations is always lower, except for n equal 1. It is always lower than in the shell model. So if we have same quantities which give the same Reynolds number scaling, but we have to take a smaller exponent in the 3D Navier-Stokes equations, it means that the shell model displays a weaker dependence on the Reynolds number as far as the velocity derivatives of order greater than 1 are concerned. Now, before moving to moments of these derivatives, let me just allow me a short digression. There exists also for the Hn a second set of differential inequalities which relate Hn and Hn plus 1, where now instead of having the infinity norm of the gradient, we have the infinity norm of the velocity squared. So this can be rewritten in this way. And since we have a perfect knowledge of this phi n, which, let me remind us, it's related to the forcing. And since we have a pointwise estimate for the energy in terms of the Grashof number, by using these two ingredients in this equation, we can also obtain point-wise estimates for the Hn themselves in terms of the Grashof number. So the existence of an absorbing set for these quantities, it was shown already in this paper by Levant, Konstantin, and Titi. What we were able to do by using this alternative ladder inequality is to estimate the radius of this absorbing set, which is therefore not only a time averaged estimate, but also a pointwise one. After this, let me come back now to our original problem, which is to discuss higher order moments of the velocity derivatives. So now I'm considering the nth derivative, but to the power 2m. So I have a new sequence of quantities labeled by n, integer n and m. And this is such that when m is equal to 1, I recover the earlier Hn. Now the proof within the shell model is completely trivial because we have this simple relation. Hnm is controlled by Hn to the power m. So I can simply use the estimates I had for Hn in a simple way and get this estimate for the general case of the nth derivative raised to the power 2m. And I again get to this Reynolds cube scaling with this exponent, which now depends on m and n, obviously. And once again, it's a high Reynolds number result, which holds very well in the simulations with different orders of differentiation and different moments. In a similar way, in a similarly easy way, one can also obtain a result for the sup of the velocity derivatives, which would be the infinity norm of the nth derivative of u. And there is an analogous scaling here reported only this case, but it works well also for higher orders. So let us now use this result again for a comparison with the 3D Navier-Stokes equations. Since there was a difference already at the level of m equal 1, we are not surprised that the difference carries over also to higher moments. And indeed, when we consider the Navier-Stokes analogs of these HNMs, which are space integrals of the nth derivative of u to the power 2m, through a proof which is much more difficult than the one for the shell model, we obtain these two estimates, which once again are comparable, but with two different exponents. And once again, the exponent for the Navier-Stokes equations are smaller than the one for the shell model, except for the case n equal to 1, which means that the shell model and the 3D Navier-Stokes equation display the same dependence on Reynolds at the level of the energy dissipation, but for higher order derivatives and higher order moments, the shell model is always weaker in the Reynolds dependence. So how can we explain this difference? So if we go back to what I said earlier, the strategy that we used, the approach that we used was really concentrated to the study of these inequalities, which allowed us to estimate higher order derivatives by using what we know about the lower ones. And I said initially, they have the same structure. And I said, I can move, if I time average, I can move Hn plus 1 on the left-hand side in both cases and estimate the right-hand side based on what I know. But here comes the main difference. It's how these two terms, this one and this one, are estimated in the two systems. Indeed, in the shell model, the sup of Kj Uj is controlled by the entropy to the power 1/2. Whereas in the Navier-Stokes equations, the infinity norm of grad u is controlled by this product. So the 1/2 exponent here needs to be shared by some h1 and some hn plus 1 of a higher order. And this is the reason why we obtain these two different dependencies on the Reynolds number in the two systems. So at this point, one can say, well, can you then find something else which is equivalent to the shell model equation, a version of the 3D Navier-Stokes equations which are closer to the shell model? And well, it turns out that if we supplement the Navier-Stokes equations with this assumption, with this constraint, so we assume that the gradual in infinity is approximately the same as, I can replace it with the gradual in L2, which means the largest value of the gradient are comparable with the standard deviation. Or in other words, I'm suppressing large fluctuations of the velocity gradient. So if I do this, instead of having the gradual infinity here, I replace gradual in L2 here, then I get exactly the same inequalities I have for the shell model. So I can manipulate them in a similar way and apply consistently this assumption, and I get that the exponent in the estimates are exactly the same then. So as far as the behavior of the velocity derivatives is concerned, the shell model is comparable to a 3D Navier-Stokes equation where the large deviations of the velocity gradient from the mean are depleted or suppressed. So this holds for the estimates of the velocity derivatives. Unfortunately, the same doesn't carry over to the case where we look at the velocity moments without any derivation. If for these ones, we again have estimates for the Navier-Stokes equations, which can be rewritten in this way. If we take our velocity gradient averaged Navier-Stokes equations, we can calculate the 2mth moment of u, use the Poincaré inequality, and use the dominance between different norms to reach this point, where we can then replace our constraint, our assumption, which leads to this inequality, which is a kind of generalized Sobolev inequality, in the sense that the Sobolev inequality would hold only for n equals 3. Here, by doing this approximation, we're assuming that the same inequality holds also for our larger m's. So if I do this, I obtain this estimate for the mth moment of the velocity, where the exponent now is greater than that of the 3D Navier-Stokes equations. However, if I look at the shell model, so the equivalent of the 2mth space moments, it's again very easy to show that H0m is now controlled by H0 to the power m, and H0 was nothing but the energy, so U squared, so Reynolds squared. So I obtain the same exponent in the time average, but with a lower power law in the Reynolds number. So this is again perfectly reproduced by the simulations. And the reason is that if I really wanted my approximate version or modified version of the Navier-Stokes equations to give the same behavior as the shell model, I would have again to suppress the very large fluctuations, not only in the velocity gradient, but also in the velocity through an approximation, through a replacement like this one. So at the level of the energy moments, the dependence on Reynolds of the shell model is much weaker, not only than in the Reynolds that in the 3D Navier-Stokes equations, but also in this velocity gradient averaged Navier-Stokes equations. So now I'm almost done. I would like to conclude with a kind of exotic result, which is maybe just a curiosity, but it's quite intriguing. So at the conclusion, at the end of his talk, John showed a further generalization of his initial result in d dimension. And he showed that the moments of the derivatives of the velocity indeed, dimensions have this scaling with this exponent, which depends on the dimension d, and it is a rigorous result for integer d 3, 2, 1, where 1 is the Burger's equations. Now, if we take the exponents for the shell model in the same estimates, we obtain that these ones coincide with those of the d-dimensional Navier-Stokes equation when d is equal to 0. So as far as these quantities, the velocity derivatives are concerned, the dependence on Reynolds of the shell model is the same of a zero-dimensional Navier-Stokes equation or a Navier-Stokes equation on a point. Given that the shell model doesn't have a spatial structure, it's a kind of scalar system in some sense. It's a kind of nice curiosity, if not, probably not more than this. So I'll come now to the conclusions. So the main message in this talk was that the shell model and the 3D Navier-Stokes equations display the same, have the same Reynolds number dependence at the level of the energy dissipation rate, but the dependence is much weaker for the shell model when we move to higher order derivatives of the velocity or moments of these quantities, or just moments of the velocity. And for the velocity derivatives, the shell model is rather equivalent to a Navier-Stokes equation where we have suppressed the very large fluctuations of the velocity gradient. And with this, I would like to conclude and to thank you for your attention.
Well, thanks a lot, Dario. That's an absolutely beautiful talk. We're blessed with 2 great talks. So I think we'll have some questions for you. Let's see. So I got one from Charlie. Well, why don't you speak up, Charlie? I mean, I can read it, but...
Oh, I just asked you, Dario. Yeah. Have you looked at the dynamics of Gevrey-like norms? You know what I mean by Gevrey norms?
Yes, yes.
I think, right? You know, the idea there to probe the exponential range of the spectrum, or the very, very high shells, and perhaps see what we would refer to as dissipation range, intermittency, and so on.
Mm-hmm. No, I haven't. It's an interesting suggestion, of course, but no, I've not done this. I know about the results in the paper by Konstantin, Levant, and Titi on the Gevrey set for the Gevrey regularity for the velocity, but I've not looked at this point. It's a good thing to look at, indeed. Thank you.
This is Uriel.
Oh, go ahead, Uriel.
Yes, I know that Alexei Maillet-Abef has a question on this problem, which can be discussed either now or in the general discussion on Friday night, whatever.
No, yeah, please.
Why not? Okay.
Yes.
Well, Alexei.
Thank you. So Dario, thank you. Very interesting. So my question is that I think that there is a possibility that this match between exponents between this shell model and Navier-Stokes may have to do with interpretation of the norms themselves, because sometime, like I think 5 years ago, I had a work which put the shell model in direct correspondence with PDE. So for you can write the Sabra shell model, which exactly corresponds to the Burger's equation in one dimension with non-local nonlinearity. And when you do this correspondence, it's not actually UN are not Fourier components, and actually you have to slightly redefine UN with some prefactor, and also you have to redefine lambda, which gives different exponents. So I wonder, maybe you may be interested to
look. I know your work. Now, I would say, on the one hand, if you tell me that it is equivalent to a kind of Berger's equation. John has showed that already it's a one-dimensional system, so there is already a different dependence in the Reynolds dependence. And on the other hand, I cannot exclude that one can reformulate things in a different way, but if you see the proofs are really the same thing as what you do in Navier-Stokes, really the same thing. I mean, there isn't anything particularly new in the shell model.
Yeah,
so
I see.
Instead of using Cauchy-Schwarz for functions, you use it for integrals. You use it for sums. It's really this.
But the results you use for Navier-Stokes, are they would be identical for example, for 3D Burgers, for example? Is the difference from what you use for Navier-Stokes from what you?
Burgers, I don't know. I don't know. This I don't know.
Because you can, I remember that it's all, I did a correspondence with one-dimensional burgers, but I guess it's possible also to relate three-dimensional burgers with like spherical symmetry and so on. So what I think my message is that the mismatch between exponents maybe has a root somewhat deeper in a definition, in a way how we compare shell model.
The problem with energy conservation in more than one dimension. So there will be some difficulty.
You see, the energy conservation is the same for Navier-Stokes and.
No. Multi-dimensional Burgers equation had an energy conservation problem in more than one dimension.
Okay.
Exactly.
There's some paper by Gorbatov and myself on this a long time ago.
Thank you.
Okay.
I see this as a critical point. What I mentioned earlier, this is quite a big difference. That in the shell model you have this, which you, I mean, this if you want, which you don't have in Navier-Stokes. This, I believe, it's a serious difference.
Yeah. Along the lines of Alexei's comment, if you would like to look for the analog of PDEs, because in the shell model, we are in the interaction between the modes. We don't have a convolution, but rather a very localized convolution in the wave numbers. Then if you go back, this kind of like will lead, if you think about it as local product, will lead to some kind of convolution in the spatial space. And this is remind me of the trick of Leray. Leray, when he wanted to prove global existence for 3D Navier-Stokes, he looked to the Navier-Stokes and he did convolution with the transport part of the velocity, which is smoother, which will allow you to get estimates of this type supremum that you have. But then they depend on the regularization. So you can regularize with some kernel. And then probably the comparison would fit much better between shell and Leray version or regularization of Navier-Stokes. That's my comment, which is along the same lines of Alexei what mentioned. And when you do the Leray regularization of the transport part, Uriel, you will have conservation of energy.
Aha, yes.
Because it's still incompressible.
Yeah.
Okay, thank you.
There was a question from Bérangère. Bérangère, if you want to...
Yeah, I have a question. So very interesting talk, by the way, Dario. Congratulations. I have a question regarding the result. So you say that in spirit, the gradient of the shell model are equivalent to the gradient of a smoother version of Navier-Stokes because you kill the large gradient and you kill the large velocity. So from a physical point of view, I would expect that the intermittency in shell model would be smaller. And it doesn't seem to be the case. So how do you reconcile these two things?
Yes, you're right. I don't know, in the sense that if you look at the energy dissipation rate, indeed you see this the same time series as you would see in the Navier-Stokes equation.
Well, you cannot compare a compressible and an incompressible thing. It just makes very little sense.
But yes, surely. But yes, I don't know about this, because I think what you're saying is that quantitatively the magnitude of intermittency is the same in the two systems, right?
Yes,
In the dissipation range.
Mm-hmm.
So I guess
no,
it's
I
really
mean, if you compute the scaling exponent of the structure function, as far as I know,
but that's inertial range. So I guess maybe the better question is, what about the dissipation range behavior? So this is related to Charlie's point about the Gavret regularity and looking in that exponential decay range where you have dissipation range intermittency.
Yeah, that might be maybe the reason. Yes.
I see what you mean. Okay.
Yeah.
Are there any other question for Dario?
But it's a very interesting question, and I suppose that some of the things arising from Alexei's talk and Dario's talk can be perhaps discussed again in the final discussion.
Mm-hmm.
Okay. So very good. So if that's where we stand, so I think we've had a great session. I mean, as far as I'm concerned, I was very impressed by the two talks. So I guess we can probably break for now and reconvene tomorrow, same time, unless somebody wants to say something. So if not, we'll just thank again our speakers and see you tomorrow.
And the chair also.
The chair didn't do very much. The thing was taking care of itself. So, it's ideal for a chairman. Okay, gentlemen, ladies and gentlemen, we'll see each other tomorrow, right?
Yeah, thank you.
Bye.
You too.
Good night.
Unless someone wants to take